Alright, so today we're going to talk about position times and time graphs. Remember that position and displacement, those terms can be used interchangeably. Alright, so a motion diagram represents the motion of an object over a given time interval. Motion diagrams can be simplified by using a particle model, and in the particle model the object is presented as a single dot. This simplifies the diagram. So when you guys did your car and buggy challenge, for the buggy that had constant velocity, you made dots representing its motion over time that are equally spaced, because the motion was uniform. A coordinate system specifies the precise location of an object. We are going to use an XY coordinate frame. So we're going to eventually get to where we throw objects up, and then of course they'll come back down, and then we're going to throw some things at an angle. So position versus time graphs, position or displacement is plotted on the y-axis. Time always goes on the x-axis no matter what. So to draw the graph, we're going to do the best fit of the recorded points. We're not going to connect the dots. We're going to do the best fit so we have a nice straight line. And a position time graph will allow you to estimate the position of objects even though there are no data points. And the motion of more than one object can be represented on a single position time graph. There we go. Alright, so when you have a steep slope, I hate this part, that means that you're going to have a large position change in a short time interval. Okay, so here we have a steep slope. The positive steep slope means that the object is moving away from the starting point, and a negative slope means that the object is moving towards the starting point. A shallow slope indicates a small position change over a long time interval. Alright, so here you can see that it's taking quite a few seconds to get change the position. And then no slope on a position time graph indicates that the object is not moving. Okay, so over time it's just staying put. Alright, so what you guys will be asked to do is to find object's velocity and describe its motion using a position time graph. So this first segment, the object is moving away from the origin. Here it's stationary, it's not moving. And in the third segment, the object is moving toward the origin or the starting point. So the first thing we're asked to do is to find the object's velocity between 0 and 5 seconds. So we want everything to the left of this green line. Alright, so velocity is equal to the change in position over time. So our final position is 5 meters. Our starting position is at 0. And then the time interval is 5. And we are looking for velocity. So we're going to do V equals 5 minus 0 over 5. So that's going to get us that V is equal to 1 meter per second. Okay, because remember that the change in velocity is VF. I'm sorry, that's not what I meant to say. The change in position is xf minus xi. Let me erase these squiggles here. Okay, in what direction is the object moving between 10 and 12 seconds? So between 10 and 12 seconds, it's going to be everything to the right of this red line. So here, the object is moving towards the origin. So it's going back to where it started from. Nice. All right, next graph is when is the object stopped and how do you know? Well, the object is stopped in 3 places. Here we go. Between A and B, C and D, E and F. So A, B, C, D, E, F. How do we know that? Because the slope of those segments is equal to 0. Okay, got a nice horizontal line. When is the object moving the fastest and the slowest? So the object is moving the fastest during the steepest slope. So this squiggly orange line is where it's moving the fastest, BC, and you can say that it has the steepest slope. And then when is the object moving the slowest? Well, it's still moving, so we're not concerned about where it's 0. The slowest is going to be from D to E, and we know that because it has the most, what's going on? Shallow slope. Okay. Come on. There we go. Next thing that we need to do is to calculate the average speed during the 25 seconds. So since we're doing speed, we don't worry about, we just have to add up each segment. All right, so we are calculating the average speed during the 25 seconds. So what we need to do is find out how far the object went during each segment. So from segment 0 to A, the car, or whatever it is, went 10 meters. From A to B, it went 0. From B to C, that doesn't look like a 0. From B to C, it went 10. Now, because we're looking for speed, we don't have to take into account that negative velocity. Okay, so that the negative direction rather we don't care about because we're looking for the speed, not the velocity. All right, then from C to D, that's 0. From D to E, that is 5. And then from E to F, that's 0. So we're going to add up all those distances. 10 plus 0 plus 10 plus 0 plus 5 plus 0 gives us a distance of 25 meters. Our time is equal to 25 seconds. So we're looking for the speed. So you can see where I'm writing on the thing. We're going to do S equals D over T. So S is 25 over 25, which is 1 meter per second. Okay. And then for number 8, we want to do the average velocity. Okay. So remember, average velocity is the change in position over time. Okay, so we don't care, when we're doing velocity, we don't care about what's going on here, right? All we care about is where did it end and where did it start, okay? So the final position is at 5 meters. The starting position, that's not an X, is at 0 meters. The time is still going to be 25 seconds, and we're looking for velocity. So velocity is equals the final position minus the starting position divided by time. So when we do 5 over 25. Sorry, I'm running out of room here. We're going to get, let's see, 0.2 meters per second. All right, so this is pretty much what we're going to do with graphs in this segment. So stay tuned.